Okay, so now we're talking about double integrals over more general regions, whereas before we had only rectangular regions. So the first thing is that we have these nicer regions than a completely general region, where you might be able to describe the integration over x or over y. So these regions where you can easily integrate with respect to x are called regions of type 1, and when you can easily integrate over y, those are regions of type 2. Notice that with regions of type 1, you have that you have an upper function and a lower function, and the bounds are kind of neat. So they are like line segments like this, or maybe they are individual singular points. Uh, and we have kind of the opposite happening with regions of type 2. You have a function that is lower with respect to, say, the x value. So lower meaning more to the left, and upper meaning more to the right. Okay. Sweeping over y, you can then compute an integral over this region or over this region, and you can see that the end values are flat like that, or individual points. So mathematically, they can be described in this way. So this is a description for a region of type 1. X goes from A to B, and Y is bounded by some function involving X, and some function involving X there. So Y is bounded above and below by two functions, G of X, G sub 2 of X, and G sub 1 of X. You can see that these regions are in fact described, or they can be described in this way. And for regions of type 2, the x and y are reversed, basically. So instead of x going from A to B, you have y going from C to D. And instead of y being sandwiched between functions of x, you have x being sandwiched between functions of y. Yeah, horizontal lines versus vertical lines. I think that's something that I emphasized here also. Okay. Now, Fubini's theorem is essentially the same as in the rectangular case. It's just saying that this notion of taking a two-dimensional integral over taking an integral over a two-dimensional region can be described as an iterated integral. You end up the fact that these two things can be equated is Fubini's theorem, and it's just that when we construct an iterated integral for a region of type 1, we will want the integration with respect to y to be inside. So pictorially, it is as though we are. It is like we sweep over y first inside, and then we subsequently sweep over x. So that is what this iterated integral represents. Like, I suppose I could just actually draw this off to the side here. So for a region of type 2, or type 1, for a region of type 1, it would be something like integrating by sweeping over in this manner. Whereas, I don't like using red for that. Whereas for a region of type 2, it would be more like you have a function like this, and maybe a function like that, and okay, fine. You have cutoffs like here and there, and then the way you sweep is you, I guess you'd sweep in that direction, but then for the x's you go this way. Whereas with regions of type 1, you end up sweeping over x in this way as your outer integral, and upwards for your inner integral. That is pictorially what is happening with these iterated integrals. Hopefully that's fairly clear what I'm saying. Okay. So here's an example of this, I guess. So suppose you have integral, you're asked to integrate this over this region. So notice that this is a this is expressed as a region of type 2 because you have y sandwiched by some constant values and x sandwiched by functions of y. So, pictorially, we have this kind of situation. So notice that although you could integrate with respect to x on the outside, y on the inside, meaning that your integration order would look like this. You could do that, but you'd have to split this region into two pieces. You'd have to split it here because the the lower function changes uh, from this uh, portion to that portion. The lower function changes, which means that you'd have to split the region into two, and then you'd have to compute two separate integrals and then add together to get the result. So that would require a bit more work if you were to do the integration in that manner. Instead, if you treat this as a region of type 2 and you integrate first with respect to, the way I'm phrasing it is not great, but the inner integral is with respect to x and the outer integral is with respect to y. So in this order, the order of the integration is dx dy, whereas over here it would be dy dx. Okay, dy dx. So right, yeah, here dx means that we sweep along the line, and then dy means we sweep the line along the region. And so the whole thing, the whole region gets swept over if we iterate in this order. And now let's look at what that computation becomes. So this is the abstract notion of integrating over the entire region D. When we specify an integration order, it becomes something like this. So you'll notice that x, it goes from the quadratic to the line, which is exactly as we would expect, right? The lower function here is this quadratic, and the upper function is this line, if we view lower and upper as being based on the x value. Okay. And so this would be the iterated integral that we would compute, that would compute this two-dimensional integral. Well, integrating this is fairly straightforward. Integrating with respect to x, this just becomes x cubed. This ends up introducing an x. And then we have to evaluate x at y squared minus 3 and also at y plus 3. Okay. Doing that evaluation, well, okay, this problem is not very nice computationally. I grabbed the problem statement itself from the book, but so if you were to plug it in, notice you have to cube things, so that's why it becomes pretty nasty, and you end up with an x to the 6th coming from this guy, as you can tell. So a bunch of algebra to get to this point, which I'm suppressing. But then this is a polynomial in terms of y, and so we can easily integrate with respect to y. We end up with a polynomial, and then we would have to evaluate at the endpoints. And if you do that computation, you get this result. Okay. So something that the book mentions, which I didn't bother to write up an example. You don't have something like this in your homework for some reason, but it's that if well, okay, I mentioned it in passing here, right? If you want to split your region up, you could then sum over the split up portions. So that's what this theorem is signifying, right? You can split your region D into smaller regions, D1 and D2, and perhaps they are easier to express the integral in terms of. You would then do these integrals separately and then add them together to get the final result. So that is one thing that you can do with these types of problems. If your region is not cleanly represented as a region of type 1 or type 2, not sure what is an example of that. I think I can come up with an example. Maybe if I stick a box next to a trapezoid. Yeah, so if this was your region, right, then, well, we can't really view this as a region of type 1 or of type 2 because there's a particular, uh, uh, what do you want to call that? This point is not smooth, so this upper function changes if we view this. Uh, um, if we try to integrate with respect to x on the outside, then the upper function would be this, and it's not. It changes right at this point, so um, it's not easy. You can't represent it as a type 1 integral. And you also can't represent it as a type 2 integral because that would make the lower function would change. The lower function with respect to y would be this diagonal followed by this line. And so this region is not cleanly represented as a region of type 1 or type 2. But if you subdivide it into the box and the trapezoid, then you can easily integrate it as a region of type 1 or of type 2. Either one would work. Okay. Let's see. Right, so this is an important topic, which I spelled integration wrong. This is an important topic, which your problems. I don't think your problems emphasize this. So, the fact that sometimes you are presented a problem with a particular integration order, but it turns out that that order is not the easiest order to use. So in this example, we integrate with respect to y first, followed by x. If we were to do it in the order that is presented to us, well, integrating with respect to y is pretty straightforward. This doesn't have a y involved, so it's basically a constant. Integrating with respect to y will give us a y popping out, which you would then evaluate from 0 to 2 minus x squared. That is just going to give you this. Okay. Well, maybe instead of just speaking all of it, I can show you what I mean. So it would become this times y, and you would evaluate y equals 0 to 2 minus x squared dx. And so you would have this evaluation. When you do the evaluation, this just gives you a x times 2 minus x squared times e to the x squared, all inside the integral dx. And then if I expand that out, I get this. Okay. Now this integral is doable, but it's bothersome. Yeah. I mean, the way I would do it is probably I'd have to split the function into two parts, and then one of them will be a u sub. One of them I think is straightforward, but it's a bit involved. But instead, one thing you can try to do is sketch the region that this integral is actually describing. Okay, so this region, x ranging from 0 to root 2, and y ranging from 0 to this function. If you sketch it, then you will end up with pictures like this. So the way that it's described, you went through x as your outermost integral. So it is described as a region of type 1 with this particular kind of arrangement. So, but notice that this region is simple enough that you can rather quickly change the integration order. If we do so, notice that we have to change the function. So the function, if instead of integrating with respect to x on the outside, if we integrate with respect to y on the outside, we go from 0 to 2 for y, but then we have to describe the upper and lower bounds of x using functions of y. Okay, so this forces us to solve this for the other variable. So we well, it looks like a few things are being done. If you swap y to the other side, the x squared, and then you take the square root, you end up with this. So that describes the upper function. And so swapping the integrals will result in this kind of transformation to the bounds of integration. One comment I should make about how these limits work. You want to think of the inner integral as having, how do I want to say this? When you're inside this integral of y, it's as though y is treated to be like a specific constant. And so this ends up depending on whatever the value y is. That value of y is coming from the outermost integral. Okay, so there's like a dependency. This inner integral depends on the outer value y. Right, and so one way I can describe this is I can say that these integrals are coupled together. Right, the integral of x depends on y, and so you can't just split things apart, unlike in the rectangular region case. See, if these were rectangular, it wouldn't have to bother with this kind of transformation. But because here, right, the integral for y depends on x, when we try to transform, or when we try to interchange the order of our integration, we end up needing to solve for things. And we can't just arbitrarily split things apart because there's a dependency. This inner integral depends on the outer integral, so we can't just split them apart automatically. All right. Now swapping the order, we can then integrate this. So you should be able to spot that this is rather straightforward to do. It's a quick u sub, right? So if you let u be x squared, then du would be 2u. That means you need to introduce a 1/2 in order to integrate. You end up with this as, okay, let me write that out. So we're talking about this integral, and you can kind of you should be able to easily spot this, right? That is the integral. And so with this definite integral, we would evaluate x from 0 to root 2 minus y. Okay. Doing that evaluation gives you this. And then you can proceed to integrate with respect to y. The negative shows up because there's a negative will come from the integration of the exponential function. And then that, I just end up absorbing the minus from this term. This would be a minus y, and then you can factor out the negative from both terms, and you get this expression. And then we evaluate y from 0 to 2. And if we do the evaluation, we get this result. Okay. So the point of this example is that sometimes you may want to reorder your integral to make the problem more doable. Okay, it can happen, although you don't see it in your homework problems, I believe. This is rather typical in an exam problem, that the order of the integration may not be the optimal one. Okay, and then last topic, I believe, before the similar problems. This is basically a carryover from the rectangular regions stuff. So area can be measured by a double integral over your region if you integrate the function 1 over the region d. And the average value, right? So the only difference between these formulas and the formulas in the previous section is that in the previous section we assumed the regions were rectangular. Here we just take them to be arbitrary regions in two-dimensional space. But you notice that there's actually no change to the formulas themselves, right? 1 over the area multiplied by the weighted the double integral of the function, which is just like the weighted sum of the function, effectively. Okay. So similar problems. It wasn't possible for me to interleave this with the text. The problems just seem they don't seem structurally representative of this topic. Okay, you have this double integral over some region. Function is cosine of x. So I believe I changed the function and I changed the triangle. But yeah, you have a very similar type of problem. So let's see. Let me first, I have to at least depict this triangle so that you can follow the fact that I'm able to set it up in 2 different ways. So pictorially, we have the triangle. So we have the point 0, 0, 3, 0, and 3, 3. So your triangle should be different than this, but it's quite similar. So this is the region D. Maybe I can label it 3 here and 3 there. So notice that there are two ways that we could set up this integral, that we could sweep over this region D. If we had our outer integral as x, so then x ranges from 0 to 3 like this, and then the lower function would have y equals 0, the upper function would have y equals x. So we could end up with this setup. Okay. Alternatively, if we view this as, I guess, a region of type 2, so this order would be thinking of it as a region of type 1 because the outer variable we sweep over is x. If we sweep over y on the outside, then it's a region of type 2. If we did it in that way, sweeping over y on the outside, then on the inside, our upper function would be y equals, or not, x equals 3, and our lower function would be x equals y, which gives us this, these bounds for the integration. And then what you might notice is that the latter one is easier to compute. So let's just see what happens if we were to use the first one. So this is rather nice, because maybe you would have initially thought like to do the first one. Well, if we did it the first way, this would end up being, because you're integrating with respect to y, you'd get a cosine x times y evaluated from 0 to x dx. So the inner integral ends up just popping an x into the, this is what happens if you compute the inner integral. It will just pop an x in because there wasn't a y, and so then evaluating will give you this this x. And now, in order to do this integral, well, you should know how to. It's an integration by parts problem. You would have to differentiate the x, integrate the cosine of x. And so it's certainly something doable because you learned integration by parts in Calc 2, but it's a few steps, right? Instead, if you were to if you were to use the other integration order, then it is rather, well, it avoids integration by parts. So integrating in this order, if we integrate with respect to x, we get integral of cosine of x is sine of x. You evaluate x equals y to x equals 3. So then we can plug in 3, we get sine of 3, we can plug in y. We get sine of y, the minus. Then we integrate this with respect to y. This is just a number, so we end up popping a y out. And then integral of negative sine becomes cosine. You evaluate y equals 0 to 3. And yes, plugging 3 in, you get these two terms. Plugging in 0, this becomes 0, you get 1. So minus 1. Yeah. Maybe just to complete this, let me just quickly do the calculation and see how much work is necessary if we were to have done it in the other way. So integral with cosine becomes sine of x, and then this becomes negative cosine of x, plus minus plus. This would end up being x sine x plus cosine of x evaluated from 0 to 3, if we were to do integration by parts. And so then you end up with 3 sine x plus cosine of 3 minus, plugging in 0, you get 0 plus cosine of 1, which is 1. Okay, so you do get the same answer, but you have to use integration by parts if you did it in the other order. So, I don't know. Perhaps it's debatable whether this order was easier. But, let's let's say it is. Okay. Another example. So, yeah, you're given something kind of like this. You would have functions in the inner integral. And it wasn't, in your problem, it's not worth it to change the order of integration. You can just do it the way it's given. I know that this one is a bit messier than the one that you're given. Let's talk through it. So integrating with respect to y, this term, you'd have a y squared over 2. Then the 4 will cancel with the 2, and so you end up with 2xy squared for that term. And then this one, you integrate with respect to y, you get y to the 4th over 4, which gives you this term. And, well, you are supposed to evaluate y equals x cubed to, or oh, cubed. I think that should just be a typo somewhere. I don't know which one I typoed. X cubed to square root of x. Let me think. I think yeah, this has to be cubed because this is a 12th, so this is a 3x cubed. Okay. 6th, 7th. Yes, yes. So when you plug this in, you get a 2x squared, and then you get a minus 1/4 x squared, which gives you a 7/4 x squared. If you evaluate at x cubed, you end up with 2x to the 7th and 1/4 x to the 12th minus. All of that is being subtracted because that's the second evaluation. So you end up with this, yes. Okay, then integrate this polynomial with respect to x, so that should be straightforward, and then evaluate. The numbers are not so nice, but you get the idea. Let's see. We have a region bounded by these equations, and then you want to find the area. So to find the area, you integrate the function 1, and this is a picture of the region. So I changed up the functions themselves. So notice that this region has a particular integration order that you'd want to use. Okay, you would want to on the outside you'd want to go sweep over x, and your inner integral you would want to sweep over y. You don't want to do it the other way because the lower function would change. It would go from this line to the y-axis. So instead we have our outer integral being with respect to x. Our inner integral well, has a lower bound being the parabola, the x squared minus 1, and the upper bound being the line, the x plus 1. That is part of the equations that bound the region. Okay. And because we're trying to compute the area of this region, we integrate the function 1. Right. So the first integral is pretty straightforward. Right, it's just 1, so integral is y. We evaluate. Yeah. And then simplifying, you get this. And then, well, this is a polynomial of x, so integrate that with respect to x. Should be pretty easy. And then evaluate. And yes, as I'm saying here, if you wanted to use the other order, if instead of dy dx, you did dx dy, if your outer integral was with respect to y, then the region would have to be split into two separate regions. You'd have to split it like so. One region with lower function here and upper function there, and then the other region has the same upper function, but the lower function is that line. So it's easier to not do it that way. Okay. In the next example, we're asked to find the average value. And something convenient about this, which is the same as in your homework actually. The function and the region are the same as one of the previous problems. So it'll be the same as your exercise 5.78. So I just copied down the information here. So the function was cosine of x, and the triangle was this triangle. So all you need to do, well, okay, maybe I should sketch the triangle. So the triangle is 3 here and 3 there. To calculate average value, you would, f average was 1 over the area of the region multiplied by the double integral over the region of the function, right? So you just have to remember that, that fact. And, well, in the previous exercise, or well, previous example, we computed this double integral. It was this in parentheses. So all we need to do is divide by the area of the triangle, of the region, which, well, it's a triangle, so it's 1/2 base times height, which gives you that the area is 9/2, and we reciprocate because we're dividing by the area of the region. Okay. I think this is the last example. Yeah. All right. So this one is maybe a bit hard to visualize. So you're given. I think I only changed this line and this line. Or well, I guess those are planes technically. They are describing planes. In 3 space. So the thing is that when you see the equations x equals 0, y equals 0, and z equals 0, those are describing the coordinate planes in 3 space. Right? They are describing the actual coordinate planes. So in some sense, it's a little redundant to say that the solid is situated in the first octant, because these equations, well, I suppose it forces the region to be in some octant. Okay, so maybe it is clarifying that to specify it's the first octant. Fine. Now notice you have the z equals 10 and z equals 0. So that makes me think that whatever this object is, it's sandwiched between these two planes at z equals 0, which is this one here, and at z equals 10, wherever that is. So somewhere up here. It's sandwiched between these two planes, this solid. And if we now if we look at it, how do I describe this? From the top, if we look at it above the z, from the positive z-axis down, so that our space looks like this, then this equation is describing a line. If you set y equal to 0, then you have that x is equal to a third. So you have this point on the x-axis. If you set x equal to 0, then you have y equals 1/5, which I suppose is a little bit closer. So you have this point. And this is a line, so you connect these 2 points. Okay. And so now, bringing this back up to 3 dimensions, this is describing a plane. Okay, this is describing a plane that is, it's a bit hard to depict here, but it's something like that. And so the point is that the solid that is being described is this that has that looks like a triangle, but then has an extra z dimension to it. So this is a triangular prism, or prism, yes, triangular prism, which is what I specified here. And then, of course, the problem is asking us to calculate the volume. So this actually doesn't use integration whatsoever. We can just resort to geometry. So it's the base of the prism, which is going to be 1/2 times a fifth times a third, and then multiplied by the height of the prism, which is specified by the extent that you extend in the z direction. So from z equals 0 to z equals 10 means that the z height is 10. And so you end up with this these numbers that you multiply, and so the volume is 1/3. Okay, and I guess that's it.